we just have to unfold one step. So recxm evaluates to a weak head normal form W, just when m with recxm substituted for x evaluates to W. And again, we have divergent term. And now there's an even subtler distinction that we can make, with not just one kind of call by name language. There's kind of idealized call by name, which is exemplified in the PCF language that Gordon Plotkin introduced. And then there's a kind of slightly messier call by name, which corresponds a bit more closely to the way that a language like Haskell works. So I think Miranda was probably closer to PCF, and then Haskell has a slightly different theory. So in PCF, we only observe programs of ground type. So we can't. So now we can take our notion of observation to be: are you a closed program of type nat which converges to a particular natural number, or we can just say, are you a closed program? Do you terminate at all? And that turns out to give us the same notion of observational equivalence. So for PCF, we only observe a ground type. So you're not allowed to distinguish programs of functional type by running them and seeing if they both converge. You have to plug them into a bigger context that at the end of the day will give you a natural number or divergence, and just compare those. So in PCF, it's the case that lambda x.m applied to n is equal to m with n for x. So this looks better, okay? So we haven't got this funny lambda v rule anymore. We've got the unrestricted beta rule that we had for the pure calculus. And similarly, first of m1 and m2 really is observationally indistinguishable from m1 in PCF. We have the full eta rule for functions as well. So lambda x mx is observationally indistinguishable from m. And in particular, omega, so a divergent computation of functional type, is observationally indistinguishable from this guy, which is quite patently not a divergent computation, lambda x dot omega. Okay, so this is the function which itself is evaluated. This is a weak head normal form, but whenever you apply it, it diverges. And this guy is a divergent computation of functional type. And so you can see that in the operational semantics, you're really, if you were tracking reductions through, you could really see kind of different behavior happening between these, if you plug these two different expressions into a larger context. But the key insight is that on your way to producing a result of ground type, in PCF, the only test you can ever make of the function is to apply it to a value. You can't evaluate an expression of functional type and see if it terminates or not. You only do that because you applied it to a value and you were interested in the answer. And in that sense, these two things are indistinguishable. Okay? So under all those tests, you're going to get the same result. So in Haskell, that's not the case. Haskell has a whole bunch of things. It's got slightly strict pattern matching, it's got a seek thing, and it's got a top level that lets you type an expression of functional type in. So if you have observation of termination at all types, then these identifications break. You can tell the difference.
If you were to eliminate those strict forms, would Haskell then only have
yeah, I mean, you can do it. So back in the 1980s, there was much wringing of hands over all this. I always think of it as sort of the war of the bottoms. There were lots of arguments about exactly how how strict pattern matching should be, and Miranda went off and tried to take the very pure line, and Haskell was a little bit more pragmatic and threw more stuff in, perhaps not always realizing what the effects were. So so one side effect of this, as I guess many people know, is that Haskell is named after Haskell Curry, and the currying isomorphism doesn't actually hold in Haskell, which is slightly embarrassing. Okay, so in Haskell, anyway, we don't have the eta rule for functions, and nor do we have the eta rule for products. I should say, nor do we have them for coproducts either. So the equational theory of Haskell is really pretty messy around the edges. Okay, so these languages, we can also give denotational semantics, and here we'll do this also in using complete partial orders, and we've got a bunch of choices as to how we're going to do it. So first choice, we can use pointed omega CPOs and strict maps. So this means domains that all have a bottom, and this is the call by value language. So domains all have a bottom, and all the functions we consider preserve that bottom. So we'll interpret the type of integers as the set of integers with a bottom stuck underneath. We'll interpret functions in the programming language as strict functions from the meaning of the argument to the meaning of the result. So this means functions that preserve the bottom. We interpret pairing in the programming languages by this smash product of pointed CPOs. So here you have a CPO meaning of A and a CPO meaning of B, and they've both got a bottom. And you take all the pairs that you can make from a pair of an element of the meaning of A and element of B. And then you identify all the guys which have a bottom on either side. Okay, so there's only one bottom in this. Switch the two together. And likewise for co-products, we take the meaning of A and the meaning of B. We stick them next. They've both got a bottom, and we stick those bottoms together. We glue them together. So this is a partial order with a bottom, and this is a partial order with a bottom. We fuse the two together. Meaning of a context will be this big smash product of the meaning of all the types in the context, and then the meaning of a term will be a function from the meaning of the context, a strict function from the meaning of the context to meaning of the argument. Or, instead of using pointed omega CPOs and strict maps, we can, just as we did for the wild language, we can use omega CPOs which don't necessarily have a bottom and put explicit bottoms in the places where we really need it. So this is nicer, this is more true to the theory of the language, because it makes a distinction that we'll make much fuss of between values and computations a little bit more apparent. So the meaning of the type of integers will just be the set Z considered as a trivial CPO with the order x is less than y if x is equal to y. But then we'll interpret functions, A arrow B, as continuous functions from the meaning of A to the lift of the meaning of B. So the intuition here is you're a call by value function. The things you get past have already been evaluated. So you don't need to make a fuss about what you do if they diverge. You just say what you will do with each value that you get passed in. But your body is something which is a computation, something which may itself diverge. So you take values which are unlifted into computations which are lifted. So now, for products, we interpret the values of product type just by the Cartesian product now, without any fuss about bottoms. We interpret co-products just by the honest-to-goodness disjoint union of the two CPOs. We take the big ordinary product of the meanings of all the types in the context. So these are all going to be values, so we're just going to take a big product of those. And then a whole term is something in general which might have some divergent behavior. So that will be a map from the meaning of the context into the lift of the meaning of the type. So now, when we give the denotational semantics of this, I'm not quite sure if this bottom line shows up, we have to do a bit of work. Just like we had to squish the meanings of functions from A to B lift and B to C lift together in the wild language, we have to do the same thing here. So the meaning of a lambda abstraction, we take the meaning of the body of the function, it goes from the meaning of gamma cross the meaning of A into the meaning of B. So we curry that, apply the currying isomorphism. This gives us something which goes from gamma into the meaning of A arrow B, which is, should be meaning brackets here, A arrow B lift. And then, because the meaning of a general expression has to be lifted, then we have to inject from the meaning of B, from A arrow B lift into A arrow B lift. So we take the currying of the meaning of the body, and then we apply this lifting operation. And then now when we come to do application, we're going to have the meaning of the function expression, the meaning of the argument expression. So we take the context, we take the meaning of each of those, the meaning of the function, the meaning of the argument. That gives us a function, A arrow B lift. So this is the potentially divergent evaluation of this function M. And then the argument, the potentially divergent A. Then we have to do a little bit of magic. We've got two bottoms here and we can't quite apply anything. And we have to shuffle this bottom out. We have to say, well, if we've got a bottom on either side, then bottom. Otherwise, we've got two values. And I'll explain what goes here in a minute. That lands us up in A arrow B lift cross A, all lifted. And now we can use this extension operator on the application. So application of A arrow B lift cross A gives you something in B lift. And that will take us, at the end of the day, into B lift. Okay, so we have to do some surgery on exactly where the bottoms come, and we'll talk about that a little bit more carefully. But also notice here what I did. I played a little shorthand trick here. I didn't say first evaluate M and then evaluate N. I said evaluate the two things in parallel. Give me the meaning of M and the meaning of N together. And this is going to be something which we can't normally do. This is going to work for this language which only has lifting, because it turns out that so we're going to end up in a bottom here if either of these guys diverge. And if either of these guys diverges, then we don't care who was responsible for that divergence. So that means we can evaluate the two things in parallel. But if they have some other kind of side effects, we'll see later that we have to be explicit about the order in which those side effects happen. But lifting, potential divergence, is something where the order in which it happens doesn't really matter. It's just the fact that it happened at all. Okay, so for call by name, skipping forward a little bit more quickly, we can do the same kind of thing, but we put the bottoms in subtly different places. So for PCF, we'll interpret that in CPOs with bottom and continuous maps. So the meaning of int is just the lift of z. The meaning of AROB is just now simply just continuous functions from A to B. The meaning of products is just products. The meaning of co-products has to have a lift added. For the Haskell-like languages, we have to put extra lifting in to correspond to the extra distinctions that Haskell can make over PCF. So now the meaning of a function is the continuous function space from A to B with an extra bottom on the outside. Likewise, for pairs, we have an extra bottom on the outside. And for co-products, it's the same as it was before. So if we have some other side effects, like global store, we can play the same kind of game. So this is a sort of ML-like language with references like they were in the while language. So we assume x and y and so forth are just global integer references. So we now have an expression bang x, which reads the variable x, and x gets m, which will assign the value of the integer expression m to the variable x, and returns no useful result. And the operational semantics works with configurations of a state and an expression to be evaluated. So if we look at the operational semantics for application, it's kind of quite complicated. We start with configuration with s. So we're interested in whether m applied to n in state s evaluates to v primed in state s triple primed, tertius, I suppose. Then the way we have to do that is we have to evaluate first the function, which makes a state transition, and then the argument, which makes another state transition to return a value, and then we substitute the value for the variable in the body of the function that was returned, and we make another state transition at the same time, and that's the result that we get. So we have to thread this state all the way through, making very explicit what order the evaluation of first the function, then the argument, then the value of the argument substituted into the body of the function happen, and we have to thread the state through to make that ordering explicit. So this language there are various other equations that don't hold once we've added this over the equations that had already failed because we'd added potential recursion. So here's one of them. So this thing says lambda x, lambda y, x paired with y applied to m and n is now distinguishable from lambda y, lambda x, x, y applied to n and m. So here the evaluation of n and m will take place in different order, and you'll see that these two things are different when we have store, whereas they were the same when we just had potential divergence but no storage effect. Okay, so denotational semantics of this is like a combination of the semantics we did for the while language with the semantics that we had before for the pure language. So the key point here is that the interpretation of a function type, AROB, now becomes a function from the meaning of A, the argument, cross store. So you have to give me a value and the store that you're in, and you will return a result and the new store that you're in. So now we have to do the threading through in the denotational semantics, just as we did in the operational semantics. So the meaning of a pairing, mn here, well, it's x, y, and s double primed, so these are the two values, where n in state s primed gives you y and new state s double primed, where m in state s, the original one, gave you value x and new state s primed. And here's this denotational semantics written out in this categorical combinators, kind of point free style. So here we just we're assembling these a chain of morphisms in here the category of sets. So here we start out with the meaning of the context and the state, and we duplicate the state to get two copies of it, the environment rather, to get two copies of it, and then we apply the meaning of m, the first component of the pair, here to gamma cross s, and this gives you a cross s, the new state and the value a, and then we swip things around a little bit to bring the a out on the outside. Now we've got a gamma cross s that we can apply the meaning of n to, and we get a cross b cross s, which is what we wanted. And we'll use this style in various places later on. So Moji's brilliant idea, and here's Moji, well, here's a very fine picture of Moji's sandals, but I can assure you that that's him behind them, was that the extra structure that we just added, and that I've laboured in some detail, the extra structure, the way we took the semantics of the pure language and massaged it to give the semantics of a language with some side effects, always has the same shape. And not only does what we do to the meanings of types, but also there's a standard uniform pattern that we're applying to the interpretation of terms to go from the pure interpretation to the interpretation when we had some side effects.